In this video, we're learning how to find the area between two curves using definite integrals. We'll go over the formulas that you'll need to know, talk about how to decide which one to use, and go over 4 simple steps you can follow. We'll then go over 5 examples step by step so you know exactly how to solve these types of problems. Be sure to download the free guided notes to follow along, highlight the formulas, and work through the examples with me. We're going to begin by learning how to set up the formula for the area between two curves and to choose whether to integrate with respect to x or with respect to y. When you're given two curves and you need to find the area between them, you're going to sum up an infinite number of rectangles with height f of x minus g of x and width dx, or with height dy and width f of y minus g of y. Summing up an infinite number of rectangles from A to B or from C to D is the same as integrating from A to B of f of x minus g of x, or integrating from C to D of f of y minus g of y. I think these formulas for the area between two curves are easier to remember if you write them as yt minus yb, that stands for the curve on the top minus the curve on the bottom, times dx, or x sub r minus x sub l, that's the curve on the right minus the curve on the left, times dy. To make things easier, I've written down 4 steps that we can follow to find the area between two curves. The first thing that you want to do is to find the points where the two curves intersect. To do this, all you're going to do is take the two curves, set them equal to each other, and solve for x. The second step is to graph the region. You'll graph the intersection points and then the two curves. Step 3 is to choose a formula. That's probably the hardest step. You'll have to choose between one of the two formulas that we just went over. This process gets easier as you work through more examples. The last step then is to just evaluate the definite integral, and you'll get a number which is equal to the area between the two curves. Let's now walk through 5 examples. In this example, we're going to find the area of the region enclosed by the following curves. Our first curve is y is equal to x plus 2, and the second curve is y is equal to minus x squared plus 4. The first thing that we want to do is to find the points where the two curves intersect. We're going to do this by setting the two curves equal to each other. So we have x plus 2 is equal to minus x squared plus 4, and we need to solve for x. Let's pull everything over to the left, and that gives us x squared plus x plus 2 minus 4 is equal to 0. So we have x squared plus x minus 2 is equal to 0. We can factor this as x plus 2 and x minus 1. And this gives us that x is equal to minus 2 and x is equal to 1. Now what we need to do is find the y value of these points of intersection. To do this, we are going to look at the two curves that were given and use the easier one. That's going to be this one, y is equal to x plus 2. So let's write that up here. Y is equal to x plus 2. When we have x is equal to minus 2, y then is equal to 0, and we get the point minus 2, 0. And then when x is equal to 1, y is equal to 3, and we get the point 1, 3. Let's go ahead and highlight these because we are going to need to plot those in our next step. Our second step is to graph the region. We're going to begin by plotting the two intersection points that we just found. The first point is at -2, 0, so we'll put that right there. And then the next point is 1, 3, and we'll put that point right here. I find that I like to wait to label these 2 points until I go ahead and get the graphs drawn. That's what we're going to do now. We are going to graph our 2 curves. Let me put them up here so we remember what they are. We have y is equal to x plus 2, and we have y is equal to minus x squared plus 4. Let's graph the line first. That is just going to go between our 2 points of intersection. And then our second curve right here is a parabola that opens downward, and the vertex is 0, 4. Our vertex is right here, and we know that it's going to go through our 2 intersection points, so we can just graph it like this. There we go. The area that we're going to find is this area in here. Let's go ahead and let's put some labels on our graph. We'll label our intersection points. This point down here is -2, 0, and this point up here is the point 1, 3. Our line is the graph y is equal to x plus 2, and our parabola is y is equal to minus x squared plus 4. It really helps to label the graphs when we go to set up our integral. The next thing that we're going to do is choose the formula for our area. We need to choose the formula based on if we want to integrate with respect to x or respect to y. If we integrate with respect to x, we want one curve on the top and one curve on the bottom. If we draw some straight lines, you can see from our graph that we do have one curve on the top and one curve on the bottom. Now let's see if we can integrate with respect to y. We need to see if we have one curve on the right and one curve on the left. If we draw a horizontal line, you can see that we have the same curve on the right that we do on the left. So we do not want to integrate with respect to y. So we are going to choose the formula. Our area is the integral from a to b, the curve on the top, yt, minus the curve on the bottom, y sub b, dx. Our curve on the top is our parabola, and our curve on the bottom is our straight line. Let's now set up and evaluate our integral. Our area is the integral from x is equal to -2 to x is equal to 1. Our curve on the top, which is minus x squared plus 4, minus our curve on the bottom, which is x plus 2. And then we have our dx. Let's now simplify our integral. -2 to 1. We have minus x squared plus 4. And then we're going to be subtracting both x and 2. I think that's the biggest mistake I see students make, is to not carry that minus sign through to both terms. This gives us a minus x minus 2 dx. And this gives us the integral from -2 to 1 of minus x squared minus x plus 2 dx. Now we can go ahead and integrate this. Our first term is minus x cubed over 3, and then we have a minus x squared over 2, and then our last term is plus 2x, and we're evaluating this from -2 to 1. Now let's plug in that x is equal to 1. This gives us minus 1/3 minus 1/2 plus 2. And then we're going to subtract off minus a minus 2 cubed over 3. We have a lot of negatives there. Minus a minus 2 squared over 2 plus 2 times minus 2. Now let's go ahead and let's simplify this. This is minus 1/3 minus 1/2 plus 2 minus, we have minus 2 cubed, which is minus 8, multiplied by a minus 1. So this is 8 over 3. And then we have a minus 4 over 2, and then a minus 4. This gives us minus 1/3 minus 1/2 plus 2 minus 8/3 plus 4 over 2, which is 2, and then plus 4. This is 2 plus 2 plus 4. That gives us an 8. And then we have a minus 1/3 and a minus 8/3. That's minus 9/3, which is minus 3. And then we have minus 1/2. So this is 5 minus 1/2. And that gives us a value of 9/2. So the area between these two curves is equal to 9/2 or 4.5. In this example, we're going to find the area of the region enclosed by the following curves. X is equal to y squared, and x is equal to y plus 2. The first thing that we want to do is to find the points where these two curves intersect. To do this, we're going to set the two curves equal to each other. So we have y squared is equal to y plus 2. Let's pull everything to the left, and we get y squared minus y minus 2 is equal to 0. We can factor this as y minus 2 times y plus 1 is equal to 0. And this gives us that y is equal to minus 1 and y is equal to 2. Now we need to find the x values for these points of intersection. To do that, we're going to use the easiest curve, and that's x is equal to y plus 2. So let's write down x is equal to y plus 2. And then when y is equal to minus 1, we get that x is equal to 1. And this gives us the point 1 minus 1. And then when y is equal to 2, we get x is equal to 4. And this gives us the point 4, 2. Let's go ahead and let's highlight these because we are going to need them in our next step. In step 2, we are going to graph the region. We are going to start by plotting these intersection points that we just found. The first point is 1 minus 1, and let's put that point right here. And then our next point is 4, 2. Let's march out 4, 1, 2, 3, 4, and up 2. We're going to hold off on labeling these points until we go ahead and graph our curves. That's what we're going to do now. Our curves are x is equal to y squared, and then x is equal to y plus 2. Let's graph the straight line first. It's just going to go between these two intersection points. Let's now graph this parabola. It is a parabola that opens to the right and has a vertex at 0, 0. So we can just go ahead and let's graph this. And we can see that these two curves enclose this area right here. Now let's go ahead and let's label everything. Our first point of intersection is down here at the bottom, and it is 1 minus 1. And then our point of intersection at the top is the point 4, 2. Let's now label our graphs. Our line is the graph x is equal to y plus 2, and then our parabola is x is equal to y squared. It really helps to put the labels on the graph for when we set up the integral. Our third step is to choose a formula for integration, and we need to decide if we want to integrate with respect to x or with respect to y. If we integrate with respect to x, we're going to have one curve on the top and one curve on the bottom. If we draw some horizontal lines here, you can see if we look at the first horizontal line that there is the same curve on the top and on the bottom. So that tells us we don't want to integrate with respect to x. Let's now see if we have one curve on the right and one curve on the left. If we draw some horizontal lines, you can see that we have one curve on the right and one curve on the left. So we want to integrate with respect to y. Let's write down our area formula. Our area is going to be the integral from c to d of our curve on the right, xr, minus our curve on the left, x sub l, times dy. Our curve on the right is our line, and our curve on the left is our parabola. Now let's go ahead and set up our integral and evaluate it. Our area is the integral from the y value of our intersection point, which is -1 to 2. Our curve on the right, which is y plus 2, minus our curve on the left, which is y squared. And we have dy. Let's go ahead and let's simplify this. This is the integral from -1 to 2 of y plus 2 minus y squared, dy. Now we can go ahead and integrate. We have y squared over 2 plus 2y minus y cubed over 3, and we're evaluating that from -1 to 2. We're going to substitute y is equal to 2 first because that's our upper limit. So we have 2 squared over 2 plus 2 times 2 minus 2 cubed over 3 minus y evaluated at -1. So we have -1 squared over 2 plus 2 times -1 minus -1 cubed over 3. Now let's see what this gives us. We have 4 divided by 2, so that's 2. And then we have 2 times 2 is 4. And then we have -8 over 3. And then for this next one, let's simplify what's in the parenthesis first. This is 1/2 minus 2 minus a -1 gives us a plus 1/3. This is equal to 6 minus 8 over 3 minus 1/2 plus 2 minus 1/3. 6 and 2 is equal to 8. So we have 8. And then we have -8/3 minus 1/3. That is -9 over 3, which is -3. And then minus 1/2. So this is 5 minus 1/2, which is equal to 9 over 2. Our area then between our two curves is equal to 9 over 2, or 4.5. In this example, we're going to find the area of the region enclosed by the following two curves. Y is equal to x squared, and y is equal to the square root of x. The first thing that we're going to do is we're going to find the points where these two curves intersect. So we're going to start by setting them equal to each other. This gives us x squared is equal to the square root of x. To solve this, we are going to square both sides, and this gives us x to the 4th is equal to x. Now we have to be really careful not to just cancel out an x, because we're going to lose a root if we do that. And we need to rewrite this as x to the 4th minus x is equal to 0. We can pull out an x, and then we have x cubed minus 1 is equal to 0. And this gives us x is equal to 0, and then x cubed is equal to 1, and this gives us x is equal to 1. So let's just write down here that we have x is equal to 0 and x is equal to 1. Now let's find the y value. We can use either curve. I'm just going to use y is equal to x squared. So when x is equal to 0, y is equal to 0. And we have the point 0, 0. And then when x is equal to 1, y is also equal to 1. And we have the point 1, 1. Let's highlight these because we are going to need these when we graph our region. And that's exactly what we're going to do now. Let's begin by plotting our two intersection points, 0, 0. And let's go ahead and let's make 1, 1 right up here. Give us a little bit more space. Let's hold off labeling the graphs and go ahead and graph our two curves. Our two curves are y is equal to x squared and y is equal to the square root of x. Y is equal to x squared looks like this. And then y is equal to the square root of x looks like that. So the region between these two curves is this region right there. Now let's go ahead and let's label everything. Our first intersection point was the origin, 0, 0, and then this point was 1, 1. Our curve in blue is y is equal to x squared, and then our other curve is y is equal to the square root of x. It's really important to label everything because that's going to make setting up the integral a lot easier. Now we have to choose a formula for our area. We have to choose if we want to integrate with respect to x or respect to y. If we integrate with respect to x, we need one curve on the top and one curve on the bottom. If we draw a straight line here, we can see that we do have a curve on the top and a curve on the bottom. Now let's see if we can integrate with respect to y. If we integrate with respect to y, we need a curve on the right and a curve on the left. And we have that as well. With this problem, we can choose to integrate with respect to x or with respect to y. I am going to choose to integrate with respect to x because our two curves were written as y is a function of x. Let's write down our formula. Our formula is the area is the integral from a to b of the curve on the top minus the curve on the bottom times dx. Our curve on the top is y is equal to root x, and then our curve on the bottom is y is equal to x squared. Now let's go ahead and let's evaluate our integral. A is equal to the integral from 0 to 1. The curve on the top, which is root x, minus the curve on the bottom, which is x squared, times dx. One thing that's really nice with these problems is if you do make a mistake and you pick the wrong curve for the top and the wrong curve for the bottom, what's going to happen is you're going to get a negative area. And if that ever happens, just know that you just go back up and switch the curves. Let's go ahead and write this as the integral from 0 to 1, x to the 1/2 minus x squared times dx. Our integral is then x to the 3/2, all divided by 3/2, minus x cubed divided by 3, and we're evaluating that between 0 and 1. We can rewrite this as 2/3 x to the 3/2 minus 1/3 x cubed, and we're going from 0 to 1. This gives us 2/3 times 1 to the 3/2 minus 1/3 times 1 cubed, and then we subtract 0, and that's always nice. This then is equal to 2/3 minus 1/3, and we get a value of 1/3. the area of the region enclosed by these two curves is equal to 1/3. I want to show you one more thing before we're done. One thing that you can do is you can draw a box like this, and you know that the area of that box is equal to 1 because each side is 1. So it makes sense that our answer is 1/3. In this example, we are going to find the area of the region enclosed by the curves y is equal to x cubed minus 2x squared plus 1, and y is equal to x squared minus 2x plus 1. So we have a cubic function and a quadratic function. The first thing that we're going to do is find the points where these two curves intersect. To do that, we are going to have to set the two curves equal to each other. This gives us x cubed minus 2x squared plus 1 is equal to x squared minus 2x plus 1. Let's go ahead and let's pull everything over to the left. We have x cubed minus 2x squared plus 1 minus x squared plus 2x minus 1 is equal to 0. Our 1's are going to cancel out, and we have x cubed minus 3x squared plus 2x is equal to 0. Notice that x is common to all three terms, so we can factor that out. And this leaves us with x squared minus 3x plus 2 is equal to 0. We can factor our quadratic as x minus 1 and x minus 2. And this gives us that x is equal to 0, 1, and 2. Now we need to find the y value that corresponds to these x values. To do that, we have to pick one of our curves. I'm going to choose the quadratic one because it's easier. So let's write down y is equal to x squared minus 2x plus 1. When x is equal to 0, y is equal to 1, and this gives us the point 0, 1. When x is equal to 1, we have 1 plus 1 minus 2, so y is equal to 0, and we have the point 1, 0. And then lastly, when x is equal to 2, we have 4 minus 4 plus 1, so y is equal to 1, and this gives us the point 2, 1. Let's go ahead and let's highlight these because these are our intersection points. Step 2 is to graph the region. Since one of our curves is a cubic, it's a little difficult to graph, so I went ahead and graphed both of these curves on Desmos. That's a great free online graphing calculator if you ever need to make a graph. Let's go ahead and let's label our intersection points. These are the points 0, 1, 1, 0, and 2, 1. We'll write that down. This is 0, 1. This point is 1, 0. And this point is 2, 1. Notice that the area between these two curves is broken up into two regions. Here's our first region, and here is our second region. Now we need to choose the correct formula to use. We need to decide if we want to integrate with respect to x or respect to y. To decide that, all you have to do is go up to your graph and draw a vertical line for integrating with respect to x. If we do that, we can see that we have one curve on the top and one curve on the bottom. It doesn't matter that the curves switch, and a different one is on the top in each region. If we want to integrate with respect to y, we draw a horizontal line, but notice in our pink region, if we draw a horizontal line at the bottom, we have the same curve on the right and on the left. So we definitely want to integrate with respect to x. Our formula then is going to be our area is the integral from a to b of our curve on the top minus our curve on the bottom times dx. Now let's go ahead and set up our integral. We are going to have two integrals because with the yellow region, our cubic is on the top, and with our pink region, our quadratic is on the top. Our area then is going to look like this. Our yellow region is going to be the integral from 0 to 1. The curve on the top is the cubic, and that is x cubed minus 2x squared plus 1. And then we're going to subtract off our quadratic, which is x squared minus 2x plus 1 dx, plus our second integral, which is going to go from 1 to 2. The curve on the top is the quadratic, so this is x squared minus 2x plus 1, minus our curve on the bottom, which is x cubed minus 2x squared plus 1, times dx. Let's go ahead and let's simplify each integral. Our first integral is the integral from 0 to 1. We have x cubed, and then we have a minus 2x squared minus x squared, so we have minus 3x squared. And then we have a plus 2x, and our 1's cancel, so that's nice. So that's just dx. And then our second integral is from 1 to 2. We have minus x cubed. We have a 2x squared and an x squared, so this is plus 3x squared. And then we have a minus 2x, and the 1's cancel. And there's our dx. We are not going to have enough space to evaluate this integral on this page, so I'm going to go ahead and I'm going to grab it and take it to the next page. Now we can do our integration. Let's integrate our first integral. This is x to the 4th over 4 minus 3x cubed over 3 plus x squared, evaluated from 0 to 1, plus, with our next integral, we have minus x to the 4th over 4 plus 3x cubed over 3 minus x squared. And we're going to evaluate this one from 1 to 2. This gives us 1/4 minus 1 plus 1. And then for our next one, we have minus 2 to the 4th over 4 plus 2 cubed minus 2 squared. And then we're going to subtract off minus 1/4 plus 1 minus 1. It's really important to write it like this so that you don't forget to multiply this negative through to all three terms. Now let's see what we get. This is 1/4 minus 2 to the 4th. That is 16, and we divide that by 4. So this is minus 4. And then we have a plus 8 minus 4. And then we have a plus 1/4. All three of these terms cancel out. We have a minus 8 plus 8, so we just have 1/4 plus 1/4, which gives us 1/2. The areas between our two curves are equal to 1/2. In this example, we are going to find the area of the region enclosed by the following two curves. We have the curve y is equal to x cubed, and we have the curve y is equal to x. The first thing that we're going to do is we're going to find the points where these two curves intersect. All we have to do is set them equal to each other. X cubed is equal to x. We need to make sure to not cancel out an x, and instead we're going to bring the x over to the left. If we cancel out an x, we lose a root. Let's now factor out an x. This gives us x squared minus 1 is equal to 0. We can factor this as x plus 1 and x minus 1. So this gives us x is equal to 0, 1, and minus 1. We need to now find the y points that correspond to these x points. So let's choose the easiest curve, and that's y is equal to x. The other one would have been fine as well. So we have y is equal to x. When x is equal to 0, we get y is equal to 0. So we have the point 0, 0. When x is equal to 1, y is equal to 1. This gives us the point 1, 1. And then when x is equal to minus 1, y is equal to minus 1. And we have the point minus 1, minus 1. Let's highlight these because these we're going to need to plot in our next step. In step 2, we are going to graph the region. Let's start by plotting these 3 intersection points that we just found. 0, 0 is here. Let's put 1, 1 up here to give us a little bit more space, and then we'll put minus 1 down there. Now we're going to graph our 2 curves. We have the curve y is equal to x, and we have the curve y is equal to x cubed. Let's graph y is equal to x first because that's easier. That's just going to be a line that passes through these 3 points. And now let's graph our cubic. Y is equal to x cubed. It bends down and then comes back up. Let's go ahead and let's label everything. Our first point of intersection was minus 1, minus 1. And then we have the origin 0, 0. And then we have the point 1, 1. Our blue line is y is equal to x, and then our red curve is y is equal to x cubed. I chose to do this problem because I wanted to show you what happens when you have 2 curves that are symmetric about the origin. When this happens, the area between the curves when x is negative is the same as the area between the curves when x is positive. Because of this, we can save some time and just integrate from 0 to 1 and then just double our answer. Let's now choose a formula. We need to decide if we want to integrate with respect to x or with respect to y. So let's go up to our graph and let's draw a vertical line in our pink region. Notice that we have a curve on the top and a curve on the bottom. That means we can integrate with respect to x. If we draw a horizontal line, we have one curve on the right and one curve on the left, so we could integrate with respect to y. I am going to choose to integrate with respect to x because our functions are given in terms of x. We can then write that our area is the integral from a to b, our curve on the top minus our curve on the bottom dx. Our curve on the top is y is equal to x, and our curve on the bottom is y is equal to x cubed. Now we can write down our area. We need to remember to multiply it by 2 because we're doubling it. So we have 2 times the integral from 0 to 1. The curve on the top is x minus the curve on the bottom is x cubed times dx. Now we can go ahead and integrate this. This is 2 times x squared divided by 2 minus x to the 4th divided by 4. And we're integrating this from 0 to 1. This gives us 2 times 1/2 minus 1/4 minus 0. So this is 2 times 1/4. And this gives us a value of 1/2. And this tells us that the area between these 2 curves is equal to 1/2. And that's it. You've learned how to find the area between curves using definite integrals, how to choose the correct formula, and how to set up the correct limits of integration based on the region. To really master finding the area between 2 curves, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.